You ever wonder what the world looks like through the eyes of a scientist? I'm not talking about, huge cosmic things. I mean the everyday stuff. The coffee in your mug, the phone in your hand. Well, today, we're going to put on our chemistry glasses and take apart something that looks super simple to find the amazing universe hiding inside. So let's jump right in.
Okay, check this out. Our subject for today, a plain old glass of salt water. Seems pretty basic, right? Water, salt, done. But for a chemist, oh no. This is a fascinating system full of different substances, properties, and all kinds of potential changes. And trust me, by the end of this, you are going to see this glass in a whole new way. So before we can deconstruct anything, we have to start with the biggest, most fundamental idea of all, matter. The definition is super simple. If it takes up space and it has mass, it's matter. That's it. So the glass itself, the water, the salt, even the air you can't see, it's all matter. And that simple concept, well, that's the foundation for absolutely everything. Okay, so you're a chemist, and you're surrounded by all this matter. How do you even begin to make sense of it all? Well, you start with a big sort. You divide everything into two main categories. This is the first and most important step in breaking down our world. And here it is, that first big fork in the road. On one side, you've got pure substances. This is stuff that's the same all the way through, like pure, clean water or a grain of pure table salt. They have a fixed, unchanging recipe. And on the other side, you've got mixtures. These are just physical mashups. Our salt water is the perfect example. We just took two pure substances and stirred them together.
But wait, we can go deeper. Let's zoom in on those pure substances. Turns out they come in two flavors too. The most basic form is an element. Think of things on the periodic table, like oxygen or aluminum. You just can't break them down into anything simpler. But when you chemically combine elements, they form a compound. And that's exactly what water, H2O, and table salt, NaCl, are. They're both compounds.
All right, let's hop back over to the other side of the chart. Mixtures. And guess what? They also split into two types. If the mix is perfectly uniform, where you can't see the individual bits, we call it homogeneous. That's our salt water, right? The salt just disappears and spreads out evenly. But if you can see the different parts, like, say, a bowl of cereal with milk or a handful of dirt from the garden, that's heterogeneous. And this is where it gets really practical, because you see this stuff everywhere. That cup of coffee you had this morning, if it's filtered, it's homogeneous. The flavor is totally even. But what about orange juice with pulp? Totally heterogeneous. You can literally see the solid pulp floating in the liquid. Once you start looking for this distinction, you'll see it all over the place. Okay, great. We've classified our salt water. We now have a label for what it is. But now the question is, how do we describe it? In chemistry, that all comes down to talking about its properties. So when it comes to describing anything, chemists have these two big buckets. A physical property tells you what the stuff is right now. Its color, how dense it is, its boiling point. You can measure all that without changing the substance itself. But a chemical property, that describes what it can become. It's all about its potential to change into something brand new, like its ability to rust or burn. You can think of physical properties as a substance's ID card. They're unique identifiers, like a fingerprint. Water's boiling point is 100 degrees Celsius. That's a key physical property. And the fact that salt dissolves so well in water, that's its solubility. Another crucial physical property. We can see all of this without changing the water or the salt into something else. And for a chemical property, rusting is the perfect example. The ability of iron to rust is something you only get to see when the iron itself is changing. It reacts with oxygen in the air and becomes a totally new substance, iron oxide. See the difference? The key word is change. The potential to change is the chemical property. Speaking of change, that brings us perfectly to the final layer of our chemical worldview, how matter actually transforms from one form to another. We all know the three common states of matter, right? Solid, liquid, and gas. Well, the only thing that separates them is energy. I like to think of it as an energy ladder. At the bottom, in a solid, molecules are low energy, just vibrating in a fixed spot. You add some energy, climb the ladder, and they can start to slide around as a liquid. Add even more energy, and they go flying off on their own as a gas. Okay, now get ready for this, because this one can feel a little weird. When a substance is actually in the middle of a phase change, like ice melting into water, its temperature gets stuck. It stays completely flat. Why? Well, because all the heat energy you're adding is being used for one specific job, breaking the bonds that hold the molecules together. It's not raising the temperature, it's doing the hard work of transformation. And here is the perfect real-world proof. Think about a pot of boiling water on the stove. Once it hits 100 degrees Celsius, that's it. It stays there. You can crank the heat up all you want, but the water itself won't get any hotter. You'll just make it boil faster. All that extra energy is going straight into one thing, turning that liquid water into steam. Now, of course, chemists have special names for these energy flows. Processes that need to absorb heat to happen, like melting ice or boiling water, are called endothermic. They pull heat in. And processes that release heat, like water freezing into ice or steam condensing on a cold window, are called exothermic. They kick heat out.
So there we have it. We've got all these new tools in our belt: classification, properties, phase changes. We can finally go back to our simple glass of salt water and see it with brand new eyes. Let's do it. Let's deconstruct this thing. What's its classification? It's a homogeneous mixture. What are its components? 2 compounds, water and salt. What's a key physical property? Well, the high solubility of that salt in the water. How could we separate them? Through a physical change, like boiling the water off. And that phase change from liquid to gas is an endothermic process. See? We just described that simple glass with the precision and the language of a chemist.
And that really brings us to the whole point. We took apart a glass of salt water. But this is just the start. This way of thinking about matter and properties and changes, it applies to literally everything. So right now, look around you. Your desk, your computer, the air you're breathing. What is it really?